Hello everybody. Today we will be talking about Treap with implicit key. That's what we took from the previous lecture to the next to this one. And probably we will talk about segment trees, Fenwick tree, and hash map. So what is the Treap with implicit key? Suppose you want to do an interesting operation rather than the standard let's see. Okay, good. So suppose we have an operation, take elements from move to front. So like we take elements from L to R. So kind of we are doing the dynamic array. So we have an array. And we perform an operation, move to front all elements from L to R. So we take elements L, R, and we want to do the second array such that this L and R will be at the top, then this is here, and this is here. So we want to do this separation, we kind of want to move them to the left. At first, this seems to be a very hard task to do because like our Treap only worked with the keys, and we can like what you want to do here, like in general, you want to do split and then merge in other order. So you want to split, merge that, and with that. But with the key, we already know that this is impossible to do because we only can join two subtrees, where the left one is has keys less than everything on the right. So for that, we do a little bit more complicated. So it's not really complicated, to be honest. So we will make node of the Treap. Node of the Treap to maintain two things. So we have a priority still, y, I will name it y, and we will have the sum inside the subtree. And that's it. That's it what we will have in our node. We already did this thing with the sum of everything in the subtree last time, but today this sum will be kind of our key to split. So we will do the following. So like split A and by X. We split node N by value X. If N is equal to null, then return pair null. We already did this. Then if N dot left dot sum less than or equal than X, then we want to split the we want to split N dot L. Okay, sorry. We split LR. We split N dot L by X, and then we merge it together by N dot left equals to right and return L and N. Okay, this is exactly the same as we did before. And else, we do the same, we just split the right one, but with x minus n dot left dot sum plus 1 or minus 1. And then we split n dot right equals to left and return n and r. So this is exactly the same, but this time we split kind of like we want to split exactly the first x elements. And you do just like that as we did with the sum previously. We have found, like we already did how to find the kth element. This is exactly the same, that you find the point where we should split by x. We this is why it is implicit key, because we don't know exactly where we want to split, but we will recursively understand how to split it. Yeah, of course, here what I missed here. Any ideas what I missed? So you can type in chat, for example, what I missed here, like, or you can see me. Like, a small hint that I missed something with the sum. You have no idea?
Well, I just need some time to refresh
Okay, yeah, sure.
the memories.
Sure, yeah, that's why I told you that's a little bit complicated. Like their Treap is a little bit complicated data structure. Okay, like it was enough time, I think, to think if nobody can understand. So we forget to recalc here. We have to update the sums so that they will be fine there. Not sure. That's it. That's how you split by the position x. The thing that merge will remain the same, because in merge we only compare the priorities and we never do anything with their sums. Like we just have to do a recalc there, and that's it. Like just as we did for the sum. For the sum here. So this means. So how should I write the remove to front using split and merge? It should be quite simple, but let's do this together. So what should we do?
Well, we should split by left, by right, and then merge in. Merge
So
in
we
pieces.
should what should we do? We should split by left. So we have to split our tree by left. You then say we split by that. What do we split? This is 1, 2.
Yes, where would split the second?
The second by what?
By right.
By right, okay. And then what should we do?
And then we should merge the. Well, we should merge the 3 with merged 1 and 4.
3, 1, merge 1 and 4. Are there any ideas why it is not correct? The first thing that is not really correct is that in our implementation we have the first x element. So like we should do here L minus 1 at first. This is the first, so like we do R here. Then the question is why this line is incorrect. You split the tree so that this contains L minus 1 elements and this contains N minus L plus 1 elements. Okay? And then you split it, this guy by R. So if you would think this all as arrays, so you have this delta 1, this delta 2. And this one from 1 to L minus 1, and this from L to N. Then what does the split R will do? Like it will take the first R elements of the tree. So it will take here the first R elements.
So we should do R minus L.
Yeah, so I would suggest doing other things. So I would say that we will do R here, like simply, and then you know that our subarray is in delta 1. Then we can do delta 1 L minus 1. Then we don't have to come up with crazy like calculating R plus L or R minus L. and we just merge them in the right order. So we first merge 4, this is our guy, and then merge 3 with 2. Okay. Now let's talk about different problems that can be solved using their implicit key. So kind of their main idea of the implicit key is that they allow you to split by their position, not by their key of an element, but by the position in this array. So suppose the next problem. We have an array again, and we take all elements from L to R and do the following. We will swap all even positions with the odd ones. So instead of L, L plus 1, L plus 2, we will create an array which will L plus 1, L, L plus 2, or L plus 3, L plus 2, and etc. R minus R, R. So kind of we swap only 2 neighboring elements. So do you have any ideas on how to deal with this? Yeah, and of course there is an operation. Please tell me the kith element out of that, of course, like, because you have to return something back. You are asked to get kth element. So this is again can be done with the Treap. Like the question is only how to do this using Treap, or several Treaps. That's a small hint. Let's think a little bit, and probably you will come up with some algorithm. Like I will give you some moments to think, not much, but I hope enough. So do you have any ideas?
Do we still have random priorities in our trees?
What do we have?
Random priorities.
Yeah, it's still random priorities kind. Yeah, so like to maintain logarithm and height of the tree, we still have random priorities. Yeah. Okay.
I guess somehow it could be done with getting two trees and placing elements. Well, the first element into one, the second into the other, and somehow merging them. But I didn't come up with an exact algorithm.
Okay, that's already good enough. That's a good start. So let us put all odd elements in one. So this is A1, A3, A5, etc. And the other one will be here. A2, A4, A6. You meant like that, right?
Yes.
Okay. So then, how to perform an operation? So you have to swap at some positions, like odd elements with even elements. So what it is really is in the sense of this arrays. Kind of this. This is always will be the first, this is third, this is fifth, and seventh, this is 4, 5, 6. So suppose that, like, let us do like that. Suppose that L is odd, okay? So we will have here L, then we will have L plus 2, etc. And we will finish with R minus 1. And what's happening here? So this array will maintain L plus 1, L plus 3, etc. R. So what does it mean that we swap elements at positions? Like you want that L plus first element, like kind of L plus first element will be at the position L, L plus third element will be in position L plus 2, and etc.
Maybe we could change just values of.
No, you cannot change, like, how do you change values? This will be linear, right? If you like take this one and swap, this one and swap, this one and swap, yes. This will be like kind of the complexity will be large. We want to do still in logarithm and time. So like this every split and merge operation that we did before, they were logarithm and time. So, but you know that you want to swap L with L plus, like you kind of has corresponding swaps. So what we can do using our splits and merges. Okay, I will give you the hint. We have to split here and here, and split here and here. Then what we should do?
Well, yes, I actually thought about that we could split them and change their places. And
yeah, exactly. You just swap these two and then merge them back. So you merge this and this, and merge this and this.
Okay.
And that's how you maintain kind of, if you want to. So these guys are odd, these are even. So when you want to swap odd with even, you just split here and then like kind of merge them in another order. Like all odd elements should be in this array, all even elements should be in this array. So there is nothing really complicated here, just like the main trick is to create two two trees with odd and even. Okay, good. Then let us solve yet another task. This will be a little bit complicated probably, but I hope that you will understand how to do it. I will give you the problem and then we will try to solve, like you can try to solve it like for several minutes, then I will give the hint and like we like just do the same as we did before. So right now the operation is really interesting. So we can take their elements LR, split it here and rotate it. Kind of. So if it was AL, AR, so it should be AR, AR minus 1, etc. AL from position L to position R. So we just can rotate the whole segment. As you can see already that kind of their split is already here. So you kind of do split. Do something with this tree. They kind of rotate and put them back. Like you kind of rotate it and merge them in that order. But what we should do to do that? Okay, let me give a hint, a small hint. So typically, like this is kind of an operation on their subarray. We already did this when we, for example, when we add to all the elements some value x last time, probably you remember. We had some push operation that kind of did this, like when we get to the element, we just push everything there, and then we will stop if we don't have to go anywhere below. Okay, then I will say that we will have an additional Boolean rotate that will say that rotation, and it will be true if the whole subtree needs to be reversed, or if it's false, then it shouldn't be reversed. So kind of the operation in general, should be very easy. We just split this array in two positions. Then you say that for this node, like this node dot rotation equals to true, and then merge them in the right order. The only question is how to propagate this rotation mark below. So let us think about that. So suppose like we want to write a push operation, push n, and we have like n has rotation there. So like if n rotation, if not rotation, then do nothing. Yeah, we don't have to do anything if there is like, we don't have to rotate this tree itself, then we should do nothing. But what we will do if there is a rotation? That's there.
Well, I didn't quite understand how do we find out about rotation. So, what do you mean by we don't need a rotation?
I mean, so here is like we do split, we get like these three arrays, and we kind of say dot rotation equals to true, and then we say merge delta 1 merge delta 2 delta 3. So we just split out, we say that this rotation guy, and please merge. And during the merge and split, we have a procedure that means push, right? Like to propagate the rotation below. So if, oh sorry, it should be not rotation true, it should be like not delta to rotation. That's an interesting part, because if this node is kind of set to be rotated, we should unset it to be rotated. So If it was rotated, then we should say that there currently it shouldn't be rotated anymore.
But we should rotate inside the merge. So when we do merge, we
yeah. So kind of we like during the merge and during the split and etc. You have the push operation that propagates the rotation below. Okay. So the question is how to write the push operation in order that we kind of done with the node itself. We pushed rotation below, so kind of that this node shouldn't be rotated anymore, and like we should do everything below it. So that is why we have to implement push. So if the node doesn't be rotated, then we should do nothing. Okay, that's reasonable. If it is not rotated, then what? Then what if n should be rotated? That's the main question. So let us think. Well, this. So if you would say this is L, this is R, and this guy is n dot rotation equals to true, what we should do? Like I would ask you like how it really looks like, right? This looks like this element X left and right. So what happens if you rotate this subarray? That's kind of hint on what to do next. Did you come up with something here?
Actually, not yet, no.
Not yet?
Well,
okay.
I think we should do something and then propagate the
yeah, so how the, like, if you do the rotation of this thing, how it looks like? So it is X somewhere. What will be on the left?
everything that was on the right in the reverse order?
Yeah, it should be right in the reverse order, and everything on the right?
The left.
Okay, is left in reverse order. That's exactly what you need to do. So, on your propagation, you will do. So we save LR as n.l, n.r. We say n.left will be now, sorry, let it be like that. We say L.rotation, not L.rotation, R.rotation, not R.rotation. So this is kind of you instead of L, you will now have LR and RR. And then you swap their order. So you just say n.left equals to R and n.right equals to left, and just say n.rotation equals to false. So you just do exactly what you did here. You just you say, please rotate this guy. Please rotate this guy, and change their places. So this thing does LR, this thing does RR, and we merge them kind of in one order. So we set the left child to be the right one and the right child to be the left one. Okay, it's clear?
Yes, but I guess I need a reminder on how does it look in terms of keys in the Treap itself, because well I thought about that, but
we don't have keys here, right? We have implicit key.
So do we recalculate them?
Yeah, sure. Like everywhere in the merge and split, you have this recalc.
But here inside the push, don't we need some recalculation?
No, because the sum, the number of elements in the subtree doesn't change. So you just change some order, but the total number of elements in the subtree doesn't change. So there is no push, there is no recalc here. But of course there are recalcs in other places. Like in split and in merge you have to do recalcs, but you don't have to do this in push.
Okay. Well, I guess that we should do so, but I thought it would break something, but apparently it doesn't. Okay.
Yeah, luckily it doesn't break. That's the thing. Okay, I think that's it for implicit key. So I hope you understood how to use it and how to write it. So let us talk about the special cases of the special cases of the Treap. So we will have an array right now. So we will do the same as we did with previously. So we have an array and we have an operation plus x under some subarray. So the issue with the Treap is that their expected the time that is calculated there, their complexity, is expected to be logarithmic. So it's not necessarily to be logarithmic, plus their constant there is quite huge, it is 4. So it works, but it probably works slower than you would expect from the data structure that wants to do only adding an x or to get an L. So for that, we can do the following. We can build the binary tree on that, and do exactly the same as we did for Treap. So we will do the binary tree here. So you know that the height of this tree is logarithmic, so it's already everything fine. Then how to get an element I? It is just go in the okay, so like it's we'll talk about this a little bit later. So how the plus x operation will work. So suppose we want to add some operations from left to right. Then what we will do? We will start with the whole list. So we will start with 1n, and we want to add on LR. Then we have an operation add with LR and x. So to start with, it will be added 1n left, right. So this is the current, the current segment. At the beginning it is 1n. And in which segment we want to include an x. So if LR intersect with LR is empty, then we do nothing. So for example, like this guy is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this guy was 1 to 10. This guy is 1 to 8. This guy is 9 to 2, 10. This guy will be 1, 4, 5, 6. As you can see, as the segments that they cover it, they're exactly this. So, for example, if you want to increment on this, you just go over all the nodes that are inside this segment, but we will take only their upper one. So let it be V even here. So like it's better to do like 1, 2, 3, 4, 5, etc. Like in the to present this as the heap in the array. So like we had a heap, binary heap, where each node has 2 children. Like you can do the same here. Just increase their length to 2 in the power of n, and like do like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So we will do, when we will come to node V, we make push V. I will explain a little bit later what this push does, but it will be, to be honest, it will be exactly the same as previously. So you push V, then you say if LR inside LR, then we say v.add plus equal x. Oh, a.v. So because we're in an array, so like we kind of have a, and return. Otherwise, we will call add to v plus 1 L. Okay, never mind. Kind of if we have here LR, so that the left guy will be L plus R divided by 2, and the right guy will be L plus R divided by 2R. Minus 1 here. So we just recursively add 2v plus 1, because like this is their left child, and the left child is L plus R divided by 2 minus 1 L R x, and then add 2v plus 2, that's the right child. We did this another way, right? We have, oh no, we have 2v plus 1, exactly 2. So never mind. L plus r divided by 2 by r, L r x. So what's happening there? We just, if the current segment, like we kind of recurse over the nodes in this tree, and if the node covers the segment that doesn't intersect with our target segment, then we do nothing. If this segment lies inside the target segment, then we just say, okay, please add their x to all these elements in the subtree. This is exactly what we did with their massive operations on Treap. So we add x to their, yeah, and probably we calculate like a dot v dot sum. No. It will be in push. Sorry. Like we just say, please add to all the elements in this subtree x. And then we go to the left child. This is the left child, and the left child covers this segment, and the right child covers this segment. So, and we recursively just go there and do. So how it works, for example, here we just start with 110, like let it be better as 16, so that we will have the power of 2, and we asked for 4, 9. So we go down, we see, here we have 1, 8, and we go 1, 4, 9. We go recursively to the children. This guy is out of the bounds, so we don't have to do anything from it. Then we see, okay, this guy is in the bounds, so we should add here x. And what on the right side? We'll have this guy, it intersects with this segment, 4, 9, it intersects. So we go to the left to the right one doesn't intersect, the left one still intersects, and then we go down, 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 and we see that this guy is inside the segment, and we have to say plus x here. So the push operation is doing exactly the same thing as in Treap. So we take v, so let it be here, push v. So we take, let it be push v l r, so we already calculated the segments for which v corresponds to. So what should we do? We should say a to v plus 1 plus equal, we have plus equal a dot av dot add, right? I have av dot add plus equal av dot add a to v plus 2 dot add plus equals a of v dot add. And then finally you could say a of v dot sum equals to, plus equals to r minus l plus 1 times a of v dot add, and then you say a of v dot add equals to 0. So you just push to the left, so we kind of should add this to all the elements on the left, then add all the elements to the right, then recalculate the sum in the subtree, and set to 0, so kind of we already updated this node.
So the push happens on every end, which we call recursively.
Yeah.
I don't quite understand why do we need the push, because we do the push
No, here we don't call the push, we just update it and return. So we kind of, yeah, possibly.
Well, if the condition is not true.
Yeah, you know, probably here, I agree with you. Probably here you don't need to have push at all. In adding. In adding, there is no reason to do push. You just get and increment the corresponding shell. The push will appear in the sum. So if we will have sum VLR LR, so we want to calculate the sum on LR. So then if LR intersect with LR equals to nothing, then return 0. Then we will do push V. Then if LR intersects, if LR is inside LR, then return no, we have to do push there. Yeah. So I will explain right now. So we return A of B dot sum. V dot sum. Otherwise, we do return sum 2V plus 1 L plus R over 2 minus 1 LR. And plus like the right part. You understand why push V is here, right?
Yes.
Because we have to push everything down. The problem with push here is that if you don't do push, oh yeah, I forgot another thing. Everything is fine. If everything is fine, we should call recalc here. That's what should we do. Because we add something in the subtree, but you haven't recalc it.
Yes.
So we have to recalc it. So we have a recalc procedure that will calculate the real sum that is inside, because we increment by x somewhere, and we have to like update everything upwards that we indeed incremented it. There.
That makes sense, yes.
Yeah. Recalc will be a little bit complicated because for recalc we have to do push. Yeah, it's better, for example, to call here push V. So like every time when you get there, it's always pushed down. So like this, when you come back to recalc, you just don't have to do push on the subchildren. You just have to add sums, and that's all. Yeah. Okay, that's it. This works faster than Treap, because like this is high logarithm n plus everything is not on the nodes but in array. The problem with Treap was also that the node is in different class, in different object, and you have to jump from one object to another object. While here everything is stored in one big chunk of an array, and it works faster. Let us talk about a little bit faster algorithm for this. So this thing is named segment tree. I just thought, obviously you could do exactly the same with the Treap, but I just explained to you that you could do this a little bit faster than Treap. Okay, now it will be probably a little bit complicated if you're not familiar with with binary representations of integers. So the thing is named Pandectry. What this Pandectry will do it will allow two operations. Please add x to the element v and calculate the sum of the prefix. The first question, how to calculate the sum on the segment?
Sum on the segment of...
From L to R. So we have two operations. We can increment one element by x and ask the like the sum on the prefix.
But what is the structure?
There is no data structure right now. Kinda. We want to do a data structure that supports these two operations, like increment an element and take the sum on the range. I will implement this using the data structure that can add an element by x and return the prefix, the sum on the prefix. So like this is sum on the prefix. So what is sum from L to R then? Suppose we are given this magic data structure that supports the same add operations as we want, and that returns the sum on the prefix. Then the sum on the subarray, on the range, will be...
Oh, well, it will be sum... Oh, it is sum from L to R?
Yeah.
We want to calculate it using
the prefix sums, yeah.
The prefix sum. So it will be the sum from R minus sum to... Okay.
Of L minus 1 to be more precise. Again, like we should be a little bit careful with minus ones. So yeah. So how we will implement our data structure? So we have an array A, and we will have an array sum. What we will have an array sum at position P. So we introduce an interesting function. For each P, we will have f of P. And this sum, this one will be maintained the sum of the elements from f of P to P. So kinda, this guy has somewhere here, this guy has somewhere here, this guy has somewhere here. So like kinda we will, for each position, we will maintain the sum on some segment, which is set by some special function. Okay, what is this special function? I'm always doing a mistake there when I'm proposing it. Something is not... okay. We'll have f of p equals to p and p plus 1. This is the bit manipulation. So what's exactly written here? So suppose that P is some binary representation, so that here is a lot of ones here. So what f of P will be?
Well, it would be the number with the one, well, with the zero where there is a zero now. And
Everything here will be zero.
Yes.
Okay, good. That's it. Then we have to understand how to jump by this operation. So, like, suppose we want to know the sum of P. Then we want answer equals to 0. Then while P bigger than 0, we do the following. We get ans plus equals sum of P, and we add like P plus 1 minus 1, because kind of we maintain from f of P to P, and to so we know, so we have P and f of P here. This is P and f of P, and then we have to ask kind of for the sum of everything on the left. So we kind of decrease 1 here. Am I right? Okay, yeah, it's bigger than equal.
Is it sum from the beginning of the array to the f of P?
It's the sum till the P. So we want to. So what's happening here? We want the answer for the prefix P.
Mm-hmm.
We ask, please give me this strange sum. It will give you the sum from f of P to P. Then you decrease f of P by 1, you will get this. And then you just ask f of P here, the sum here. Then you ask for the sum here, and so on until the end of the.
And then we get the sum to P. Okay.
And this guy will be returned ans. This will be the sum of all the elements from 0 to P. Okay, the question on how to update how to make add. Okay, suppose that we want some position V where we have once, oh, sorry. Like that. So in which segments f of pp it lies? So we kind of want to propagate this change into all the segments that cover V. That's reasonable, right? So we change an element V, and we want all the FPP will be updated. Which one will be updated? As you can see, we have P and F of P, like all the trailing ones become zeros. So this means that V lies in all the kind of prefixes of V with ones at the end. Kind of if we take V prime 0, 1, just copying this here, like this will lie only in this ones and then. Because why so? Because when you like replace this ones by zeros, you will get inside. You will become somewhere in the middle here.
Okay, so how do we find the split point? By the zero? By zero?
Yeah, kind of. There is split point by zero. I will explain right now how to do this using bit magic. So we want to add Vx, and then while V less than size, like less than n, then what we will do, we will say sum of V plus equal to x, and V equals V or V plus 1. Did I write? Yeah, I did it right. So I claim that I updated all their segments that contain V.
I think I missed what is sum square brackets V? Sum of V.
Sum of V is our array where sum of x or sum of p is their sum from f of p to p. So this is why I'm kind of, I claim that by this while I iterate over all the segments that contained V. So for example, when you start with V, right? You start with V, you know that V lies in the segment f of V, right? So we add sum of V plus equal to x. Then, what is the next segment that lies where V lies? So there is something here bigger, and how this looks like, it should look like the prefix of V and multiple ones at the end. So this is exactly what we are doing here. So this plus 1 and V, this is exactly where we take this 0 by 1. We replace the 0 by 1. What does plus 1 do? So if the node was, if V was that, then new V will be, I don't know what's here, 0 or 1, doesn't matter. So here we have 0 and 1 and 1 here. So this 0 will become 1 right now. Yeah, so we kind of replace all zeros with ones, starting from the right. And these are exactly the segments that contain V. So that's it. That's the whole data structure that supports like sum, calculate the sum of the elements, and increment some element by x. You can do this. You can do by that simple two-dimensional data structure. So, for example, we have a grid, and you have an operation add to some position x, y, some a, and get some from x, y, x1, yeah, so x, y. This means that this is the sum on this kind of prefix of the tree. Do I understand? So suppose you are given a rectangle. Do I understand how to get the sum on this rectangle given this prefix.
Well, you're using the prefixes also.
Yeah, using prefix, like kind of these two-dimensional prefixes. So we want, for example, in this rectangle.
We should do split it into 4 parts and then subtract and add them. Well, the top left part we should find this sum.
Mm-hmm.
We should find the very top
Mm-hmm.
thing. We should find the left thing and subtract the angle from them. Well, and subtract it from the whole thing.
Not exactly, very close, but not exactly. So we have to. We subtract from this. We subtract exactly this, as you said. We subtract exactly this, as you said. But you have to increment by that. So we shouldn't decrement 3 times. We should two decrements and 1 increment, because this one is calculated 2 times increased, 1 time increased and 2 times decreased by that. So, and still the same, we have this sum x, y equal to the sum on this strange rectangle where this x f of x, y f of y. So kind of we do exactly the same. So, and instead of 1 while, we will have 2 whiles, like while and while, and here is while and while by choosing, like, if it is kind of x here, then while y bigger than 0, we do x like this thing, and we do y with the same thing. The same goes with the add. So like kind of we can simply go from 1-dimensional to 2-dimensional grid with this. And this Fenwick tree works even faster for the separation than segment tree, of course, because like there is almost nothing to do here. Okay, any questions for today's lecture?
Is that right that we can do this for any number of dimensions?
Yeah, any number of dimensions. Yeah, you just have to do like nesting loops inside one each other. Yeah, that you can do for any dimension. Oh yeah, I haven't said about the complexity, but it is, I think, kind of understandable that this is logarithmic complexity. Kind of this guy is always replacing each 0 with 1. That is in the binary representation. So this will work logarithmic. The same is with this. So we always increment the number of 1s that are at their suffix or the representation.
Well, yes.
Okay. Thank you for coming, and see you next time.